Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I think the guys are supposed to come.
You're going to crash it
Ah, okay.
But I don't think it happens with that camera. I think it happens with a bigger camera.
That's crash. We're going to crash it.
Maybe down or something? I don't know. Yeah.
That's right.
I think it's on.
You think what? It's on, yeah, that's my guess. So it's a great pleasure to introduce David Gamarnik from MIT, who's going to talk about correlation decay in statistical physics.
Thank you.
And you have to let them know there's hundreds of people watching from the determinist. Yeah.
I can feel that.
You can feel it by the... you can go right now, the Jumbotron.
The screen was also speakers showing.
Okay, Dmitris, thanks very much for this opportunity. I've never been to Microsoft, and I didn't realize that you have this kind of hooking up system to stadiums and everything. It's always been impressed by technology. So today's talk falls right in the middle of two things, statistical physics and algorithms. And I'm not saying that there is nothing in the middle. There is a lot in the middle. But we just want to take it a notch further. And so this is a joint work with Antar Bandyopadhyay from the University of Chalmers in Sweden. So let me just quickly remind you what the counting problem is. There's many incarnations of it, but sort of one of the typical setting is you have some combinatorial problem, and instead of finding the optimal solution on a set of combinatorial in the combinatorial space, you want to find the cardinality of the feasible space. And one way you can set it up is to set up some kind of an integer programming problem where you have a bunch of linear constraints, and you look for the space of all solutions which have which are integral, which satisfies these constraints. And many problems will fall into this category, like finding the number of full matchings in the graph, finding the number of independent sets, coloring, feasible solution to bin packing, satisfiability, etc. But some problems of the counting nature don't fall here. For example, the volume computation. And of course, that's a difficult problem. And Valiant introduced this sharp P class. But it turns out that many interesting problems can be solved approximately. And here the method of choice is the rapidly mixing Markov chains. And it's been quite a successful method, and actually broke quite a few interesting problems, including computing permanence and the volume of the convex body and many other interesting problems. So what we're going to do for this talk, let me actually run by you pretty much the entire talk in just several sentences. And the idea is this. It turns out there is a connection between counting and the sampling in the following sense. Let's say we want to count the number of independent sets in the graph. Okay? Let's say I pick up a vertex in this graph and ask, well, among all the independent sets, well, what is the probability that this particular node belongs to the randomly chosen independent set from the space of all independent sets? Okay? So that's some kind of a probability. It's called the marginal probability. Turns out that if you can compute this marginal probability, then you can compute approximately solve the counting problem by picking the vertex, computing this probability, taking inverse, throwing away the vertex with the edges, taking another vertex, and doing the same thing, and so on. So in other words, sampling and counting is sort of equivalent. Okay? And that's why Markov chain method actually, how the Markov chain method does. It computes approximately these marginal probabilities by constructing some Markov chain dynamics. So what we want to do is compute these marginal probabilities via different methods, pretty much directly, assuming the graph has some special structure. The special structure is locally tree-like structure. Turns out in many interesting cases we can do that. And therefore we can relate, we can do approximately solve the counting problem via direct methods. There's two issues here. First, how we actually can compute it directly. If your graph was a tree to begin with, if it was a tree, computing this marginal probability is a trivial problem. Just whether maybe you know that or you could just guess that it is. It's just a simple recursive computation on a tree. Okay, if it's locally tree-like, you can still pretend it's a tree and hope that it's actually close to the true value. The marginal of the entire graph is close to the marginal on the tree. It will be the case provided there is some kind of independence from the boundary of the tree. And that's where statistical physics helps. So if we know that there is something which is called the correlation decay, independence from the boundary, then we can solve this on the tree and do this recursive procedure and do the estimation of the total count. Okay? So that's essentially what we're doing. It turns out that this studying the independence of the marginal from the boundary is a well-studied problem in statistical physics, and there is lots of results which are established in this domain. So we're just taking this result and using it for counting. There is an extra feature to this problem, which is we want to actually say something more concrete in the special cases when the graph is regular. Then there is a difficulty is when you remove the vertex, you destroy regularity. But it turns out that there is a relatively simple fix to this problem as well. And I will show it in this. And it turns out that for special cases of regular graphs, not only we can compute approximately, solve the counting problem approximately, we can get the pretty much exact limiting values. I'll explain that. But I just wanted to tell you what we're doing here. That's the connection between statistical physics and counting. And if you followed me thus far, you might as well leave now because nothing else I'm going to tell you. Everything else I'm going to tell you is just details. If you followed thus far, that's pretty much the essence of the talk. But come back 5 minutes before the talk because I will say something about a different problem, the feasibility, not counting problem. So nobody's leaving, so that's my comment was irrelevant. So in this talk, we will focus on two counting problems. Given the graph, compute the total number of independent sets and the total number of Q colorings. Okay? And we want to do it without using the Markov chain technique. So let me start with the weaknesses of our approach. And there's several important weaknesses. So let me highlight those weaknesses. First, as it turns out, we compute approximation to something which is actually the logarithm of the total count. So the total count, the total set of feasible solutions, is also called the partition function in physics. Let's say it's z. So what we can do is we can approximate log of z. That's weaker as opposed to Markov chain method, which actually can do epsilon approximation to the z itself. Okay, so that's one weakness. And the class of problems for which we can apply is thus so far is limited. Coloring, independent sets, we want the graph to be low degree, and we want it to have large girth. In other words, the size of the smallest cycle is very large. In other words, the graph is locally tree-like. Okay? So that's a weakness. But there's an advantage. Well, first advantage is obvious. It will be obvious because our approach is deterministic. It's not based on sampling. It's more direct computation. But the second thing is that it turns out that we can get explicit results in the special case of regular graphs. Okay? So let me give you a couple of results that we get. And couple of slides later, I'll just give you more or less a full set, but just to start. So for example, consider class of 3 regular graphs which has large girth appropriately defined. It turns out that the number of independent sets in this graph is approximately given by this quantity. This is some quantity which we compute numerically from some fixed point distribution, from some fixed point solution. Numerically, it's this value raised to the power n. That's the number of independent sets in any 3 regular graph with large girth independently from the graph. So that's sort of an interesting point because it says that this quantity does not depend on the actual underlying graph. This is not something that you can get from Markov chain sampling because there is a sampling error. Another thing is that if you look at again, our regular graph with large girth and look at the total number of Q colorings in this graph, when we make Q bigger than R plus 1, so that to guarantee there is always at least one coloring. So this is just a trivial condition for making sure there is at least one coloring. And it turns out that, in this case, the total number of coloring is given by this quantity, simple quantity. When we looked at that, we thought, this sounds too simple to be true. But there's a way to do the sanity check here. Here's the sanity check. Imagine that your regular graph is actually uniformly random. Take a random regular graph and use the first and second moment method. It will give exactly this result. Okay? So formula is at least correct in this setting. But what we're saying is that this is true in arbitrary or regular graph in large girth. It doesn't have to be random. And the first and second moment method, for those of you who know, and it actually uses the randomness of the underlying graph. And there are immediate implication of this result to random regular graphs, which basically says that the partition function for the hardcore, well, I'm using this sort of statistical physics terminology, but basically it says that total number of independent sets in 3 regular graph with large girth, random regular graph, converges to the same quantity as here. Okay, so let me just give you briefly basics. So we will consider the counting the number of independent sets and colorings, but also we'll consider some modifications. In particular, we will consider partition functions. So what are we doing? Let's fix the parameter lambda greater than 0. It's sometimes called the activity, sometimes called the inverse temperature. And consider then the partition function on a graph is defined as this sum. We sum over all independent sets in a graph, and we take the lambda to the cardinality of the set. That's a partition function. Okay. Now, when lambda is equal to 1, then this is just 1, so this is just counting. It's just the total number of independent sets. When lambda is equal to infinity, that's a uniform distribution on a set of largest independent sets in the graph. That's the regime we don't consider. That's actually the most difficult regime, most interesting, but much harder to analyze. It's actually not analyzable yet. Okay, for coloring you can do the same thing, where you fix parameters for each colors and weight each color by products of lambda to the number of nodes colored with particular coloring, get the partition function. But for this talk, we will only consider the case where all the lambdas are equal to 1. So it's just z is just a counting. Okay. And the Gibbs distribution is defined using the partition function like this. The probability that we select a particular independent set is proportional to the weight of this independent set, which is just the weight divided by partition function. And the same thing for coloring. Okay. Now here's the, I've touched on this a little bit, how you connect sampling to counting. And you can use the following simple observation. Physicists call it cavity method, but here's what it actually does. Let's suppose we select our independent set according to the Gibbs distribution. In special case, that would be uniform distribution. And we ask, what is the probability that a particular node does not belong to this independent set, okay, with respect to Gibbs distribution? And you can work out the algebra here, and it turns out, for a very fairly simple reason, that it's a ratio of partition function of the reduced graph minus this node. I'm sorry, this should be V. Graph minus this node V, and the partition function of the entire function. Okay? It's a fairly simple observation, but it's extremely useful because now you can write down your partition function as a product of inverses of these probabilities when you remove vertices one by one. Okay? So as a result, if you want to compute this, you need to compute these probabilities. And that's where Markov chain sampling method, what Markov chain sampling method does. It computes these probabilities approximately by sampling. But we want to do it a little bit differently. Oops. Okay. So let me say now let me state our results basically. The first is for independent sets. Okay, so there's epsilons and deltas here, but let me say what we really do. For every graph which has degree 4, not necessarily regular, any graph which has degree 4 and large girth. We propose an algorithm which computes the total number of independent sets in this graph approximately. And the approximation is on the log scale. In other words, for every epsilon there exists a sufficiently large girth such that the girth of your graph is bigger than g, then this is true. Okay? And this is something that we compute efficiently. Now for coloring, it's even simpler. So we fix constant r, which is the largest degree, and q, which is the number of colors we want to use. And it turns out that in order to compute approximately the total number of colorings, what you need to do is the following thing. You keep doing this reduction of the graph. And in every step, you look at what is the degree of my current vertex v in the remaining part of the graph. And then plug it in this expression, take the logarithm, and that's the answer. That's for coloring. Now in the special case of in the special case of regular graphs, there is, yeah.
Is this some arbitrary order in which you remove the vertices, or?
Yes.
So that kind of corresponds to the greedy algorithm of selecting a vertex, coloring it at random, and so on.
Correct. Yes. Yes. Well, yeah, and there is a reason for why this is correct. The reason being some correlation decay, which says that any color is equally likely to be a color. Okay. Okay. So in the special case of regular graphs, here's what happens. Now with the inverse temperature now, we want it to be less than this quantity. And this is, let me call it Kelly condition, and I'll elaborate on that. It's some condition to ensure something nice happens in statistical physics terminology, in particular that there is a correlation decay. So whenever lambda is less than this quantity, the partition function has the following limit. For any R-regular graph with large girth, it doesn't have to be random. And the quantity is this. It's logarithm of this expression where x is a unique fixed point solution to this equation. Okay? So that's what happens for regular graphs. Any questions about this? And you can get specific values here for, well, it turns out that in a special case of counting is lambda is equal to 1. Turns out that this condition holds for r up to 5 and then breaks. So as a result, we can do the counting. We can compute the total number of independent sets for degrees up to 5 now. And these are the numbers. Okay. This is a sort of a toy case. When degree is 2, there is a simple independent way to do the sanity check here and check that it's actually a correct value. Because it's a 2-degree graph, it's very easy to see how many independent sets there are. Okay. And for coloring, it's even simpler and has to do with this uniformity of the colorings, assigning of colorings to particular nodes. So basically says that the total number of colorings, Q colorings, in the regular graph has this limit, independently of the graph. Okay? Any questions so far? So what we do is we propose this three-step approach. And here it's actually only the second is non-trivial. First and third is borderline trivial. And well, let me also say that this is sort of an approach which has been taken on some disguised form in other contexts as well. For example, zeta-2 conjecture that David Ellis solved for minimal assignment problem essentially goes through the similar steps. The first step is this. You just observe that if your underlying graph was a tree, then computing the Gibbs distribution marginals of Gibbs distribution is trivial. It's just a recursive procedure, fairly straightforward. The second step is showing that if your graph has a locally tree-like structure, then the impact of the boundary disappears. And that's what we call the correlation decay. And this is really the crucial step here. And it relates to many things in statistical physics, like the Bruchian's uniqueness condition for Gibbs measure, and as I said, Aldous' local reconvergence method. Talagram has done something similar for random k-set at high temperature. So what he did was he considered random k-set in high temperature appropriately defined, and he showed that the values that you assign to particular the variables have a product form distribution under the Gibbs distribution. In other words, the probability that x1 is 0, x2 is 0, x3 is 0 is equal to the product of individual probabilities asymptotically as the size of the system goes to infinity. And the physicists have their own take on that, which is replica symmetry breaking method. Also, this is related to reconstruction on trees, because what is the reconstruction of trees? And seeing that you define some kind of a Markov chain on a tree, and seeing, is it true that label on the root is independent from the boundary? And there's many different versions of that. There's worst case condition independence, there's an average, free boundary, and so on. So philosophically, it's very much related to this to the correlation decay business. Now, third step is just to, once you establish the correlation decay, is somehow to say that your answer on the tree is the correct answer for the entire graph. And in the case of general graphs, there is not much you need to do. It's just if it's correct on the tree, it's correct. The projection is correct. What happens is that for the case of regular graphs, removing the vertex destroys the regularity. Okay, so if I take the vertex, remove it, the remaining graph is no longer regular, right? But there is a fixed. So in principle, you can compute this number, but we want to get the actual number explicitly. And there is a very simple trick by Mézard and Parisi, which basically does some kind of a rewiring and preserves regularity. They use this trick on the random regular graph, and without proving anything, they said that the new graph that you obtain after rewiring is still a random uniform regular graph. But it turns out that this randomness is not really important. You can do this trick for arbitrary graph which has a large girth, and I'll talk about this later. Okay. So there's many instantiations of correlation decay, and here's one of the simplest one, and it's also the most relevant. So look at let's say, consider a three-regular tree with some large depth g. So we have a root, then we have degree 3, and so on. And then these are sort of the boundary nodes at distance g. So here's the result from Kelly in 1985. He showed the following thing. If I considered Gibbs distribution on the set of all independent sets on this graph. Suppose I condition that all my nodes on the boundary belong to the independent sets. What is the conditional probability that the root belongs to the independent set? Well, it's some number. That's one experiment. The second experiment, suppose I condition that none of them belongs to the independent sets. And then consider the conditional probability at the root then. So two conditional probability distributions. So what he showed is that provided that this condition holds on the temperatures, in other words, the temperature is sufficiently high, turns out that both quantities are asymptotically the same as the depth goes to infinity. And this actually implies by some monotonicity argument that whatever boundary condition you put, it actually will converge to this or to this, which is the same thing. Okay? So that's the simplest example of correlation decay. Whatever you put on the boundary, the probability that the root belongs to an independent set is independent from the boundary. But that turns out not to be true when lambda is bigger than this parameter. Then these two values are not the same, and they converge to some values which are two solutions to some fixed point equation. So you can reduce it to some fixed point equation and show that in this case there's a unique fixed point equation, unique fixed point solution. In this case, there is multiple fixed point solutions. Okay? Here's the result which is relevant for coloring. And actually, after this result, our results for coloring are pretty much trivial. It basically says the same thing, the same correlation decay for coloring. It says consider any irregular graph with depth g. Okay? And look, what is the probability that the root has a particular color given some boundary condition? And turns out that converges to 1 over q. It's uniform with respect to worst case boundary condition. Okay? But it turns out that this actually, the regularity here is not essential. So if you have any graph with largest degree r, the same thing holds. It's a sort of, it's a very strong contraction argument which applies to the whole class of degree r trees. And this is also a tight result. You cannot have correlation decay under this sort of strong assumption when q is less than or equal to r. Because what happens is that when q is less than or equal, let's say q is equal to r, you can put a particular coloring which completely will enforce the coloring at the root. It's not very difficult to show. But it turns out that just one extra color helps you tremendously. Makes you complete independence from the boundary with respect to worst case boundary condition. And the reason that these results, where people were looking at these results, Kelly and Jonathan and many other, actually this problem is an open solution to something that Brightwell and Winkler posed as an open problem a couple of years before that. And they had a weaker condition for this to be the case, but it turns out this is the right condition. And the reason that it was looked at is because correlation decay implies the uniqueness of Gibbs measure on infinite graphs. That was the main goal, to see under which conditions you have a unique Gibbs distribution on infinite graphs. If the graph is finite, it's always unique. There's no issue here. But the graph is infinite, the partition function is infinity. So you have to be careful how you define the Gibbs distribution. There is a way to define a Gibbs distribution, which was introduced by Dobrushin back in the 60s. But turns out that it's not necessarily unique. Correlation decay gives you uniqueness. Okay? So what I want to do now for the remaining part of the talk is basically illustrate how would this work in one of the results that we obtained. So I want to illustrate this three-step method for the case of counting independent sets in degree for graphs with large girth. Okay? So step one is solving it on a tree. It's simple, but let me still tell you what's going on. You look at the partition function on a tree with a particular temperature lambda. So lambda is a temperature parameter fixed. And you write down the partition function as sum of two terms. One corresponding to all the summand such that the node does not belong to independent set, and one corresponding to the case when it does. And, well, if it does not, that turns out that what you obtain is the product. It's a tree, right? So if I'm saying that my root does not belong to independent set, then overall the partition function for that specific case is the product of partition functions here and here, or here. I have degree 3. Okay, that's in the case when it does not belong to independent set. If it does belong to independent set, then I have to exclude these nodes, all of them. But if I exclude these nodes, then I'm basically looking at these subtrees of subtrees. Then here I'm completely free in these trees. So I'm taking basically a product of partition functions 2 steps lower. And so then you just divide by one part, and you can relate the probability that the root does not belong to independent sets to the probability that the children do not belong to the independent sets with respect to their subtrees. As a result, you have this. It's a product because the subtrees have independent partition. They have independent Gibbs distribution, and it turns out to be this recursion. So what we want to do now is look at this function, which takes probabilities of the children and translates into probability at the root. Okay, so what we want to show is the following. No matter what is the graph, we look at the graphs which has degree 4. But largest degree 4 can have smaller degrees. Whatever is the tree, we want to show that provided that the depth is sufficiently large, no matter what we put on the boundary, the value at the root asymptotically is independent from the boundary. And that turns out to be basically equivalent to showing that f is quote-unquote contraction. It's not contraction in the usual sense because it's a function which takes k vector into one vector. But basically what we want to show is that at every next step, the difference between probabilities with respect to two boundary conditions is smaller than the original difference by some factor. It turns out to be 0.9 works. And so what we do is we do a computer-assisted proof. Maybe there is a direct way to show that this is the case. Well, incidentally, this inequality is not true on the space. X's are probabilities. They take value between 0 and 1. If you take the k-dimensional cube, that's not true. That's not true that this is less than 0.9. So you have to first observe that actually the interesting space is a part of this cube. And it turns out you have to do 2 steps and realize the action happens on the subcube of this cube. And then you want to show that actually it's less than 0.9. Maybe there is a direct way to show that, but we do it sort of numerically. But first we use the mean value theorem. The difference is at most the gradient at any point in this interesting part of the cube, absolute value minus the infinite norm. So now we want to show that this gradient is less than 0.9. The way we showed it is check that it's actually less than 0.9 on the grid, and then use the second order Taylor expansion to show that actually between the points on the grid, it's not going to change large. It's actually a very nice function, right? So it has all the derivatives in the interior, and it turns out that you can do that. So it's computer-assisted proof. You might be happy with that or not happy with that, but that's the only proof we have. Okay? Any questions? So that inequality implies that for any tree which has degree 4, there is a correlation decay. No matter what you put on the boundary, the probability at the root is independent from the boundary condition. Incidentally, actually implies uniqueness of the Gibbs measure on infinite such trees. Any infinite tree with degree at most 4 has uniform Gibbs measure with respect to when the activity is equal to 1. Okay? And the third step, as I mentioned, is fairly straightforward for general graphs. We'll look again, remove vertices one by one. And what we do is, okay, so for each current vertex, we look at the neighborhood of this vertex in the remaining part of the graph. And because the girth is large, it's going to be a tree. And it's going to be a tree with degree at most 4. So we have a correlation decay. So we know that the difference between any two boundary conditions is at most epsilon, provided that the G is large enough. That means that but what we really care is the marginal with respect to the true Gibbs distribution. And this marginal, because of the averaging of this kind of differences, is not too far from the marginal of on the tree with respect to free boundary condition. The difference is at most epsilon. So that step is, I don't know if it's obvious or not obvious, but it's really not a big deal. And that's basically an algorithm. At every point we look at the tree with sufficient depth, forget the boundary condition, pretend that we have a free boundary condition, compute the probability, the marginal probability, take the inverse, take the product, that's accounting. And that's just an algorithm to describe that. So say we wanted to apply this to regular graphs. And it turns out that, well, there is a problem. Because you remove the node, you don't have regularity. So here's a fix that Parisi and Mézard proposed. I don't know, maybe this was It's kind of very simple. I don't know if they were the first one to observe that, but they said the following. So let's say it's degree 3 regular graph. Has 3 children here. And they have their corresponding subtrees. And here's another node. So basically they say, well, let's delete these 2 nodes now. And connect them, for example, like this. Okay? So now it's regular. You restore to regularity. Well, right. So that's the question, right? Do you destroy the girth? So they don't address this question. They say, well, if you select them uniformly at random 2 points and rewire like this, they just pretend it's going to be a random uniform. And I think it is. I'm not sure. But it turns out that you don't need to do that. First, we're not working with random regular graphs to begin with. We're working with arbitrary regular graphs with large girths. And the nice thing is, turns out that if you do this rewiring carefully, you can actually preserve the large girth for arbitrary graph. And basically, what you need to do is the following. At every point, you select 2 nodes which have the largest distance. And that's it, basically. It takes a little bit of an argument, but it's not too complicated. So every time you select that, if there are very large distance, the distance should be large provided that the size of the graph is large, because the degree is bounded. Okay, so therefore, can it happen that when I connect their neighbors, the girth is very small? Well, not really, because that would mean something bad for the original graph. You have to go to a couple of cases when you create a cycle with 1 edge, or you create a cycle with a couple of edges, but let me not spend too much time here. So basically means that you can preserve regularity and large girth all the way up to the graph which has a constant size. The graph has a constant size, its impact on the Gibbs distribution is marginal on the log space. Okay? So what we need to do is basically, we need to, okay, so now we need to do then 2 things. We know how to relate, we know how to compute the impact of removing 1 vertex, the impact on the partition function. Removing 1 vertex is essentially like there's an expression in terms of partition function. But now we also need to know what's the impact when we rewire them. But that's not too complicated. So when you remove the vertex, turns out that in the special case of regular graph, the probability that the root does not belong to the independent set is 1 over 2 minus x. So let me just say what happens here. X is a unique solution to this expression. It turns out that the x is the probability that the root does not belong to the independent set in this graph. It's a 2 regular out graph. All the nodes have out degree 2, including the root. And then x is the probability that this root does not belong to the independent set. But our graph is a bit different. We have actually root has degree 3. So I have to do a little bit of adjustment. And that adjustment results that in the fact that instead of x, you have this 1 over 2 minus x. But the idea is exactly the same. Okay? Okay, so we know that if we remove 1 vertex, the impact on the partition function is this. Now if you remove 2 vertices, but they are sufficiently far from each other, then it's going to be, the impact is going to be a product of 2 because of the correlation decay. Okay? And now the final step is see the impact when we reconnect them. But the nodes that we reconnect are also far from each other. So impact on the partition function is the probability that it is not true that the probability that at least one of them does not belong to the independent set. In that case, you can put this extra edge between here and here. And that's equal to, well, it's y minus the probability that both of them belong to the independent set, so it's just this. So when you put all this together, you basically obtain that the net impact on the partition function of removing two nodes and rewiring is this quantity. And since we can perform it pretty much for the entire graph, step by step, the partition function for the independent sets has this expression. That's the limit. For any lambda where the correlation decay holds. Okay? So there's n over 2 here because we remove two vertices at a time. Any questions about this part? So actually that's pretty much sort of all I wanted to say, but let me say a little bit, a couple of extensions. Well, first is, what about sparse random graph which are not regular? And so here we can still obtain similar results, but it's just they look a little bit uglier. The first question, when do you have a correlation decay? And turns out that this is a sufficient condition. So we look at the independent sets in the sparse random graphs, and notice the probability is constant over n. Lambda is the inverse temperature. It turns out that under this condition you do have a correlation decay, and that's a Stefan-Vandenberg condition. Well, it turns out that something more than this happens. It turns out that when you do have a correlation decay, a certain fixed point, certain distributional equation has a unique fixed point, and it looks like this. So C's are random variables. So what you want is to find a random variable such that if you plug it into this expression and drawing them independently, on the output you obtain a new random variable which has exactly the same distribution. N is a Poisson with some parameter z. Turns out that when this condition is satisfied, this has, well, actually, the second iterate of this operator has a unique fixed point solution. Presuming that you could solve this distributional equation and call z or chi z is a random variable which is distributed according to this distribution, then it turns out that the partition function has this form, which is an integral of expected value of log inverse. So, computing that explicitly seems like difficult, but at least we know that the limit exists. And in some cases, just showing that the partition function has appropriate limit in the log space as n goes to infinity, that requires work. So, for example, the random k-set work of Talleyrand in the high temperature regime, that's a lot of work to actually show that. So we're actually hoping that maybe that will work for the random k-set as well in high temperature regime. We'll have no implications for the satisfiability conjecture. Okay? But here's something else. And this now has nothing to do with counting. It has to do with finding a feasible solution. So suppose you have a graph which has degree 3 and large girth. If you have 4 colors, you can always color it. But if you have 3 colors, it's not clear. You can color it, right? So we propose the following algorithm, which seems to work in simulation. And there is underlying correlation decay conjecture, which seems technically hard to prove, but experimentally it seems to be working correct. So let me explain what's going on here. The algorithm is simple. For each node and color pair, so each node and color pair, let's generate a random weight, let's say uniformly, independently, for all such pairs. And then for each node, look at its tree outgoing from this node. And just on this tree, well, there's many proper colorings on this tree. It's actually 2 colorable because it's a tree. So among all the 3 colorings, find the coloring which maximizes the weight. Okay? So we have a graph here. For every node, and we do this simultaneously. We look, for this node, we look at the regular tree outgoing from it. Actually, in this case, regularity is not important, because if you can color regular graphs, then you can color arbitrary graphs, because adding edges makes your life harder, but nevertheless. So this is a tree with some constant depth g. So each node you have, and each color you have some weight. So I want to find a coloring which maximizes the total weight on this tree. And while I do that, I want to see what is the winning color here. What is the color out of 1 and 2 and 3? What is the color that actually contributes to the maximum weight coloring? Okay? And let's say I select this color in my graph, and that's my coloring. Turns out it works, in a sense that it provides a coloring of all but little of n nodes. So almost proper coloring.
So you do this in parallel for all vertices?
And you do that parallel for all vertices. And here's the reason why, here's the sort of experimental reason why it works. Turns out that the following thing happens. When we do this computation, we have 3 weights. W1, W2, W3. What are these weights? W1 is the maximum weight when I condition my nodes to have a color 1 in this subtree. W2 is when I condition to be 2, W3 is 3. So W is actually the max of these 3 things. And actually, let's look at the differences between 2. So the first 0, W2 minus W1, W3 minus W1. So the following thing happens. Let's do 2 experiments. I generate these random weights. I compute this quantity for the original tree. But then I compute the same quantity when I remove the last level. Right? Turns out that these values, not only the winning number is the same, the values are the same. In other words, the actual values here they are disappearing in a very strong sense. Which means the following. When I look at this neighborhood of this graph, right, and I selected my winning color with respect to this neighborhood, that's some color. But it turns out if I shift by 1 level or increase by 1 level, the winning color with overwhelming probability will be the same. What does it mean? It means that I never violate the coloring constraint, because it's better to look at it like this. If this is my node, this is the boundary. If this is my node, the boundary now becomes 1 level lower here and 1 level higher here. So it's like this, right? But I just said that it actually, once I do this shift in levels, the winning color doesn't change. So it was as if I was selecting the maximizing color from these 2 nodes with respect to the same local tree. But when I was doing that, I was satisfying color. I was looking only for the for the proper colorings. So that means with the modular little bit, some nodes where this correlation actually has an impact, which goes to 0, that the graph is colorable. So the only thing here is that to be able to analyze this. So experimentally it seems to work. All these differences are the same for the 2 experiments. We just need to prove that. I don't think it's extremely hard, but it's technical work. And it seems that in a lot of this context, you write down some kind of recursive distributional equation, and you need to be able to analyze it. When does it have a unique solution? When do you have a correlation decay? In other words, the underlying dynamical system converges to the unique solution from any starting point or relevant starting point, and so on.
So question, so are you saying that every graph with sufficiently large girth is 3 colorable?
Yes.
Up to
Yes.
low then?
Yes. That would be the implication.
Kind of the argument that you say somehow should...
Sorry?
Why would it be little of n? Wouldn't it be some constant fraction which is not colored that depends on the girth?
Girth, right. So if the girth is 10, then it's a fraction. But if the girth is...
So if the girth grows as a function of
Yeah.
n, then...
Yeah. For example, if you take take a random regular graph. Of course, you have small cycles here and there, but because we allow for mistakes here, we can remove them. So it's not going to have a big impact here. And that's pretty much all I wanted to say. And what we want to do, well, we want to see, of course, is there any relevance to random k-set problem? And it seems like our approach, in principle, philosophically, it works for high temperature regime. Because in high temperature regime, you will see correlation decay. Therefore, you might be able to compute the partition function of the k-set in the random k-set problem. And this business is interesting. And actually, that applies to edge coloring as well, because here on the tree, nodes and edge coloring is sort of equivalent. And of course, another interesting question is that somehow being able to remove the locally tree-like condition, and because the uniqueness of Gibbs measure is established under more general conditions, for example, given by de Bruijn's uniqueness condition. And perhaps we can use that to design counting algorithms for general cases, not only the cases when you have a locally tree-like structure. That's the end of my talk.
Back to the question about almost coloring with 3 colors. Do you think that the number of vertices which you miss should be like n times 1 over the girth times a constant? Is that a reasonable guess?
N times 1 minus 1 over girth? The ones you missed is 1 over girth? Let's see. If the girth is g, then the probability of a mistake, quote unquote, is decaying exponentially in g. So it's got exponentially in g. But the girth cannot be much larger than log with some constant. So the best you could hope for is something like 1 over n to some power alpha. Of course, if we happen to be lucky that actually this constant exponent is better than the expansion of the graph, that would mean coloring for the entire thing, because I'm not sure that that's the case, and I don't think so. Was that the question? Okay.
And do you have an example which shows that if you remove a small fraction of the vertices, then you can two-color the graph?
Two-color? Yes. So if you remove... So the graph is it bipartite? Bipartite?
Well, almost bipartite. So
for random graph, it's far from being almost bipartite.
So for two coloring is a little bit different, right? It's not...
Maybe 4 and 3 might be better.
And perhaps maybe mentions something back to statistical physics. This computation of partition functions is sort of not exactly in this context, but similar. Was done by Mazard and a bunch of authors. But what seems mysterious is that they actually claim that they compute this counting, or actually up to any temperature. So when the temperature is 0 or infinite temperature is infinity, that corresponds to the largest independent set. So basically they claim that they compute the largest independent set on the random 3 regular graph. And the problem with that is that the only information they use from the random regularity of this graph is the fact that it's locally tree-like, and this rewiring operation does not make a girth small. But as I said, you can do that for any graph. So it seems like the argument would imply that any graph with large girth, which is 3 regular, has that value of the maximum independent set, independent of the graph. But that's not true. Because a random regular graph has the largest independent set, which is some fraction of 0.45. Well, it's not known, but there is an upper bound, which is strictly less than 1/2. But if you take a random bipartite, that's why I remember it. If you take a random bipartite regular graph, then it has an independent set which is exactly 1/2. So there must be something more than just the girth and the regularity which features in the size of the largest independent set. And that's why what physicists approach that seems a bit, I don't know, but maybe they know something more than they put in the paper, but